I would like to introduce the talk Multidimensional Stein-Malliavin calculus for Gaussian and Gamma distribution. Please, you have 1 hour and we start our seminar.
Thank you very much. Okay, thank you very much for the invitation. Okay, I'm very happy to be in touch with the Russian mathematician because it is so long time we didn't have the opportunity to discuss, and I'm happy to see that mathematics go well there. Okay, so let me explain what we did recently with my colleague Jérémy, which is connected now, and with other collaborators, okay? And about this multidimensional Stein method for Gaussian and Gamma distribution. So actually, this is the plan of my talk. I will start by explaining something about the classical Stein method, okay? Because Stein method is not my invention, it's not new. I mean, it's an old theory, okay? Then I will try to explain you what is more recent, okay? What we did more recent about this multidimensional Stein method and what to approximate, okay? And if I have time, I will discuss some application to solution to SPDEs and maybe to asymptotic independence of inner chaos. But this I'm not sure if I have time. I just want to be sure that I can explain the basic idea of this method, okay, and what we can do with this, okay? So, what is Stein method? Okay, as I told you, it's an old theory, and it is actually a, let's say, collection of probabilistic methods. And the purpose of this method, okay, is to evaluate distances between distribution, okay, between probability distribution, okay. So you have, imagine you have two random variables, f and g, and the idea is to measure how far or how close is the distribution of f from the distribution of g, okay? So this is the purpose of the method, to measure this, okay, distance between f and g. How to define the distance? I know you know, I think you know very well, okay? A general definition for the distance between f and g, okay, is this formula, okay? You take the supremum over h in some class of function, capital H, okay, of the expectation hf minus expectation hg, okay? And this, with this definition, you can cover various distances, okay? I mean, it depends what you put in this class capital H, okay, in this class capital H. For instance, if you take H to be the class of Lipschitz function with Lipschitz constant less than 1, okay, here the norm of H is the Lipschitz norm, okay, then you have the definition of the so-called Wasserstein distance, okay? If you consider H to be the class of indicator function of this form, intervals of the form minus infinity z, and z is moving in the real line, on the real line, then you have the Kolmogorov distance, okay? And for the Kolmogorov distance, you use this formula, okay? I mean, it's in the same, it's a particular case of the definition. But other possibilities, if you want to consider other distances, you can consider the total variation distance if you take H to be the set of indicator function, okay? And you can take also other distances like for Temurier, but not only these distances. There are several ways several distances you can consider, okay? Well, so this is the purpose, okay? Measure the distance between two probability distribution. Of course, you imagine we have a particular case of more significant, let's say, there is a case when one of these two variables is Gaussian, okay? For example, in this case, I mean, there are many applications for this approximation, okay? This is usually called the normal approximation, okay? Stein method via normal approximation, you can say, okay? So you have two random variables, one is Gaussian, one is not Gaussian, okay? And you have to measure the distance between them, okay? This has many applications in statistics, for example, because you always have some estimator which is asymptotically normal, but you have to quantify, okay? Quantify how far or how close is the distribution of the estimator from the limit law, okay? And I mean, this is the case of the normal approximation, but there are also other cases, okay? Other distribution of interest. For example, today we'll also discuss the gamma distribution, but there are distributions, the so-called Pearson class and so on. So, I mean, there is a vast literature of Stein method, okay? And many distributions have been treated. Well, what is the starting point of the method, okay? I mean, everything starts with a very simple observation, okay? This observation means a characterization of the normal distribution, okay? So imagine you have a random variable, consider a random variable which is Gaussian, okay? Gaussian with zero mean and variance sigma square, okay? Well, then you can characterize this distribution, okay? By the following formula, okay? By this identity here, okay? I mean, Z is Gaussian if and only if sigma square expectation F prime Z minus expectation Z of Z is zero, okay? This is if and only if the result is practically the starting point of the Stein method, okay? And so this identity is zero, okay? You have zero here for a large class of function F, okay? Here, if you want to be more precise, you need to consider every F which is differentiable, and you have integrability of the derivative, okay? Expectation F prime Z is finite, okay? Well, this is easy to prove. It's exercise for students if you want, okay? If you consider Z to be Gaussian, okay? Just you can prove this identity by just doing by hand, okay? Writing within the Gaussian density, integrating by parts and so on, okay? And there is also pretty easy argument for the converse direction, for example, via characteristic function or so on, okay? So this is easy, and this is the starting point of the Stein method, okay? Well, so what is the idea of this method? The idea of this method is now you have another random variable x, which is not Gaussian in principle, no? And you have this quantity, sigma square, expectation f prime x, minus expectation x fx, okay? Remember that this is zero if x is Gaussian, okay? If x is Gaussian, this is zero. But we can think that if for given x, okay, for given x, this quantity is close to zero, okay, then the intuition told us that x, the distribution of x, should be close to the Gaussian distribution, okay? And so many bounds will be obtained from this idea, okay? Let me show how, okay? So first step, you associate a Stein equation. What is a Stein equation? Okay, this equation, the Stein equation is the following. Sigma square f prime x minus 6fx is equal to h minus expectation hz, where z is Gaussian, okay? Well, here, h is given, okay? H is arbitrary function. Not so arbitrary because you have to assume that you have some integrability condition here. But outside this condition, okay, h is arbitrary, okay? And you need to find f, okay, will depend on h, that solves this equation, okay? Okay, so this is deterministic equation. And you try to solve this equation, and the idea is that you can, okay, you can solve the equation. Given h, you can find a solution denoted fh, okay, which is, of course, a solution in terms of h. I will give you the formula, some formula later, okay? And you can also prove that the solution is nice. Nice, I mean, you have the properties you need for later. For the moment, the solution is unique. If you consider the class of bounding solution, you have a unibounding solution, and this solution is differentiable, and the derivative is also bounded, okay? Also, this can be proved by hand, okay? Well, starting from this equation, okay, what you can do, okay? Remember that you want to measure, to evaluate, to quantify the distance between a random variable x and z, okay? What you will do, you replace small x by the random variable capital X here, and you will take the expectation, okay? And you use this identity for fh, which is the solution to the Stein equation, okay? So I will show you on the next slide what happens here. Well, So if you take a random variables f, okay, you have this identity, okay? Remember that for given age, fh is a solution to the state identity, okay? Well, so you have expectation hf, one expectation z, okay? This is the right-hand side of the previous identity, okay? So here, you replace, as I told you, x by f, okay, and you take the expectation, okay? So you have this identity here, great. And what we say, is the left-hand side here. If you take the supremum over h, you'll have the distance, okay? The definition of the distance, Kolmogorov or total variation of Wasserstein or what you want, okay? But the idea is, I don't want to calculate this supremum in the left-hand side. I will calculate the supremum in the right-hand side, okay? Well, why? Because we can do some tricks with the right-hand side here, okay? Good. So what you can do with the right-hand side? You have an integration by parts. And this is the point where the Malliavin calculus enters into the play, okay? At this moment, what I present here is the Stein-Malliavin method, meaning the combination of the Stein method, old Stein method, with the Malliavin calculus, okay? Well, so that means...
Sorry, Z is Gaussian, Z.
That is Gaussian, yes. Exactly. That's why in the left-hand side, you have the distance between f and z, okay? Well, so this, the left-hand side will be the distance between f and z, okay? Z is Gaussian, of course. And here, in the right-hand side, okay, you do some integration by parts. You write this quantity, the last expectation, as expectation of f prime f times something, okay? This something, if you are an expert in Malliavin calculus, you will recognize what it is. If you are not expert, let's just forget it for the moment. It's some quantity, okay, some quantity, depending on D, which is the Malliavin derivatives, okay, depending on L, which is the Ornstein-Uhlenbeck operator, and in fact, we have here the pseudo-inverse of the Ornstein-Uhlenbeck operator, okay? But anyway, you have f prime or something, okay? Okay. And here you replace on the first line, okay? And if you replace in the first line, you will put in factor, common factor f prime, okay? So what will you have? Maybe I will go to the next slide, yes? So the distance, which this is the distance between f, the distribution of f and the distribution of z, the Gaussian distribution. And here you have the right-hand side, you put f prime in factor, you have sigma square minus this quantity, this ugly quantity if you want, depending on Malliavin derivatives. And you remember that the Stein method has the solution to the Stein equation has a derivatives which is bounded, okay? And you just bound by f prime by a constant, okay? And you can find the bound for the distance between the distribution of f and the Gaussian distribution with variance sigma square and expectation 0, okay? This is a bound. And this is, I mean, the first idea comes from Norden and Pecati, okay? And many people use this bound, okay? This bound is good if you can calculate this quantity, Malliavin derivatives and so on. But it works very well for Wiener chaos, for functionals of the Wiener process and so on, okay? In many cases, we can compute this, and we can also prove that in some cases it's very close to optimality, okay? Well, so if you look to this inequality at the end, you don't have a supremum, okay? It works for many distances, Kolmogorov or Wasserstein total variation, okay? Only the constant depends on the distance, okay? Otherwise, this bound is available for many distances, okay? And depends only on your random variables f, okay? Well, so this is the idea of the classical Stein method, okay? As I told you, there are a lot of applications. I mean, since 10 or maybe 20 years, people work on this, and well, so now I would like to present you something more recent, okay? It's what we called multidimensional Stein method, okay? The idea comes from a work from Leandro Pimentel, okay? So Leandro Pimentel is a guy from Rio de Janeiro, okay? He's not a specialist in Malliavin calculus, but he learned a little bit just to apply for other stuff, okay? Other stuff meaning KPZ equation and so on, okay? Stuff I mean, in general, I cannot understand very well, but he explained to me that this was the motivation. Okay, so what is the idea now? It's like a generalization, just like a generalization of what I explained before. Okay, so now you want to measure the distance between the probability distribution of the couple X, Y. Okay, so X is one-dimensional and Y is d-dimensional. Okay, these two guys are in principle arbitrary distribution, correlated. Okay, and the other vector, it's the other probability, it's the probability of Z times probability of Y. Meaning what? Meaning the probability of a vector with components Z and Y, and components are independent. Okay, Z is independent of Y. Okay, well, so this is the purpose here. Okay, now. So if you look to the limit distribution, okay, there is no limit for the moment, but the second distribution, this is not Gaussian. So we are not in the context of the classical Stein method here, okay? Well, so let me show the idea here. It's just an extension of the first method, okay, but with some non-trivial adaptation and some tricky points. Okay, so you consider an operator as the operators I told you before. Okay, so this is sigma square f prime minus 6 fx, but just in addition you have a second variable which is y. Okay, which is an element of rd. Okay, so then let's start with a observation that characterizes the law as for the classical Stein method. Okay, so assume that this is Gaussian. Okay, and X is independent of Y. Then you can prove that the expectation of this operator applied to X, Y, it's equal to 0. Okay, so it's like the Gaussian characterization, or the characterization of the Gaussian law. Okay, so here, if you start with this guy, okay, well, you can prove it by hand. I think I put some idea. Just to use the classical Stein method, okay? For the classical Stein method, okay, you remember that the expectation of prime X, it's expectation of X fx, okay? So these are what I use here for every Y fixed, okay? So this identity is from one-dimensional Stein method, okay? Then you write this in terms of probability distribution, okay? Write both terms as integral with respect to the probability distribution of the X, random variables X. We remember it's supposed to be Gaussian, okay? And that's why we can use this. And we have this equality, and these both terms in both sides, we integrate with respect to the probability distribution of Y, okay? So what happens if I integrate here with respect to dpy? The following happens, okay? We integrate in respect to dpy everything, okay? You'll find here, you will have here the product probability. Remember the X and Y are independent, okay? Which is exactly the probability distribution of the couple, okay? So finally, in the left-hand side, you will find this expectation of the partial derivative with respect to X of f, X, okay, or this quantity, okay? And for the second term, okay, you do the same operation, and you integrate, I mean, with respect to the probability distribution of Y, you will find this expectation is fixed. Okay, so that means that the expectation of the operator, I come back. Okay, so this is what, just to prove that this expectation is 0. Okay, so if it's Gaussian, it's independent of Y, so this expectation is 0. But what is nice is that I can prove a converse direction. Okay, if this is 0, then this is Gaussian and independent of Y. So let me put the statement here. More precisely, you have this. Okay. You consider end of variable X. Now you don't know that it is Gaussian. You just know that it is integrable, okay? And you assume the expectation of this operator is 0, okay? For a large class of function f, okay? Large class of function f. To be exact, here you need to find, to consider functions f defined on the r power d plus 1 to r, such that f is differentiable with respect to X at least, and this derivative is bounded. Okay. Then, if this is 0, you can prove that X is Gaussian, and in the same time, X is independent of Y. Okay. So how we can do this? you can do it also by using characteristic functions. So you consider the characteristic function of the couple x, x, y. Okay, so you know very well this is the definition of the characteristic function of the couple. Okay, and if you have this, you apply. Okay, you apply the equation from the hypothesis. Okay, so the expectation, some expectation is 0. Okay, so first you differentiate with respect to lambda, the characteristic function. You have this equality which is trivial, and then you apply that the hypothesis, that the expectation of the operator is 0. So for the real part and imaginary part, okay, so you can do it for both, and you will find such equality here, okay, which is and at the end, okay, after applying the hypothesis and some trivial stuff, you find the differential equation satisfied by the characteristic function. Okay, so phi satisfies the differential equation, this one, and but this you can solve the equation. It's the easy equation, right? So you know the initial condition. Okay, phi 0 lambda is the characteristic function of the vector y. Okay, so by solving this equation, you find this formula for the characteristic function is the initial condition times this exponential. Okay, and you can deduce easily that x should be Gaussian because you have this characteristic function, and x should be independent of y because it's the product of these two. Okay, you have this product formula here. Okay, well, so this was the calculation of the law. So from this point we can continue to develop the multidimensional Stein method by following the lines of the one-dimensional method. So we have a Stein equation now. Okay, we have the operator in the left-hand side, and we have h minus expectation of h in the right-hand side. Again, z is Gaussian. Okay, and well, you have this equation. Okay, the solution will be f, which depends on h. Okay, and h is arbitrary, but in some class. Okay, here we can prove for the moment. We consider for the moment that h is bounded. We bounded partial derivatives. Okay. All the partial derivatives are bounded, okay? And then you try to solve this equation, and you can prove again that this equation has a unique bounded solution. And I think I wrote here the equation, the solution. This is exactly the solution of the equation, okay? Here's some SPC formula. And this is exactly what we have in the one-dimensional case, but in the one-dimensional case, we have no y. So this is just to have y in addition, okay? So now we can... You have to prove that the solution is nice, that is bounded, differentiable, with bounded derivatives. And we can also manage to do this, okay? So with respect to the one-dimensional method, what is new here? The new part is the differential with respect to y, okay? This is a new problem that appears, but we can manage to control this quantity, okay? And we have bounds for all the derivatives, okay? All the derivatives. Well, if we have bounds for all derivatives, we do what we did before, okay? Remember, we want to approximate these two probability distribution, probability of the vector x, y, both are arbitrary, okay? And probability of z times y. So z is Gaussian, independent of y, okay? Then, from the Stein equation, we have this identity. Okay, this is identity meaning comes exactly from the Stein equation. Fh is a solution to the Stein equation corresponding to h. Okay, and I'll do the trick before, as before. We use some integration by parts. Actually, the idea here that is that you can express x, this variable x, as something. Okay, something is delta d l minus 1 applied to x itself. Delta is score of the integral, d is Malliavin derivative, L is the Stein-Malliavin operator. This is easy formula, but very important at the end, okay? And now you can do an integration by parts between delta and d are joint operators, okay? And when you do this, we can express this expectation x fh as d minus 1x and d fh applied to xy, okay? See, this is exactly what we did in the one-dimensional case. But what is new here? When you differentiate df df here, you'll have is a chain rule. You can apply the chain rule because Malliavin derivatives admits the chain rule. Okay, so you have dx. Okay, partial derivative with respect to x times dx and partial derivative with respect to y times dy. Okay, this last line is new. It does not appear in the classical one method. Okay, so you have this, and then now you remember that the derivative is nice. So what happens? Actually, what happens if you bound the derivative but what you want, okay, by the constants that you want, you have the distance between the law of xy, the law of z times y, okay, which will be the sum of two terms, okay. The first term, it's exactly what you have seen for the one-dimensional method, okay. This first term is to quantify the distance between x and z, okay. These two, but you have a second term, and we interpret this second term by saying that this second term is to quantify the decorrelation between x and y, because in principle x and y are correlated, but you compare with something with independent components. Okay, so this second guy, which in easy cases is like constant times derivative of x scalar product with derivative of y, okay? This quantifies the decorrelation between x and y, okay? So you have a bound, okay? And this is actually the essence of the multidimensional Stein method, okay? So I have several applications, and I have some application to HPDs, but maybe I'll try to show you on Wiener chaos, some application on Wiener chaos, okay? Because I have no time to present both, okay? Well, let me go here to some application to fractional Brownian motion, okay? So consider this sequence Vn, okay? Here you have BH, a fractional Brownian motion, which has the index in 0, 1, okay? And Q is a Hermite polynomial, okay? Hermite polynomial for the Q, okay? So this sequence has, you know, the increments of the fractional Brownian motion are not independent. They are correlated, okay? But what happens? Sometimes the partial sum of the increments goes to a Gaussian distribution, and sometimes it goes to other thing, okay? So, I mean, if the correlation is not so strong, okay, then you have a Gaussian limit, and the meaning not so strong, you have to assume something was a hash parameter h. If hash parameter is between 0 and 1 minus 1 over 2q, okay, then this sequence converges to a Gaussian distribution, okay, with some with 0 mean and some variance that you can compute explicitly, okay. Well, this is Brewer-Major theorem in principle, okay, the first, but there are other many contributions at the end, okay. But what happens if you have a strong correlation between the increment? If h is close to 1, so what happens here? So now I consider this sequence, okay? You still have the increments of the fractional Brownian motion. You consider the second Hermite polynomial. Second Hermite polynomial meaning e squared minus 1, okay? E squared minus 1. So in this case, if you normalize with something different, okay, different normalization, you can prove that the limit for h between 3 over 4 and 1, okay, this limit goes to something which is not Gaussian. This is called the Rosenblatt, random variables, okay? So the first contribution comes from Dobrushin and the Peter Major, I think, in the 70s, something like this, okay? And well, this is non-central limit theorem because you have a non-Gaussian distribution at the end, okay? So what we can do with my method, okay? Just to give you an example, because I have to stop to leave my young colleague to continue about the gamma distribution, okay? And we can quantify, we can look to the vector, the conversion of the vector. So Vn, Un. So if h is in some interval, okay? If h is in this interval, so the first will convert to Gaussian, the second will convert to non-Gaussian, okay? So what we can do, we can look to the conversion of the couple. We can prove that the couple converges to the second couple where z is Gaussian. You have a vector with Gaussian on the first component, Rosenblatt on the second component, and components are independent. And we can also quantify the distance related to this approximation, at least in the Wasserstein distance, okay? So if you want to quantify the Wasserstein distance between this couple and its limit, which is this vector is not a Gaussian vector, okay? It's only the first component is Gaussian, but not the second, okay? You can quantify doing some computation, using calculating Malliavin derivatives and so on. You can have you can arrive at the end at some concrete estimates, okay? I don't know if it's optimal, maybe, but we can do something with this method. Now we try to do other applications to statistics for estimators to see estimators which are Gaussian and non-Gaussian and so on. And but this was the idea of the multidimensional Stein-Malliavin calculus. So I think maybe it's time to leave my colleague Jérémy Zurcher to continue with the gamma distribution. I don't know if you are ready, Jérémy.
We're good. Thank you, Ciprian.
Okay.
I will share my screen. Okay, can you see it? I will.
Yes, we
Yes.
see. We
Okay,
see
thank
all-
you. Right. First, thank you for the invitation, and thank you for letting me explaining what we did with Ciprian. This is okay. The second part of the talk. With Ciprian, we saw that we see a method to see how to compare Gaussian distribution with other random variables and how to apply it to show some asymptotic independence. And we will do the same where the target law is the gamma law. So here we go. The gamma law would be the center gamma law. This is a law with one parameter, which is called nu, right here. Distribution with density given by rho indexed by nu, which is given by this expression. So the goal of my talk will be the same as Ciprian, meaning that if we called z indexed by nu a random variable following the gamma distribution with parameter nu, we will compare the distribution between the couple z and y, where y is a random vector, and the distribution where z and y is independent. So the cross product between the two laws right over there. So y is a random vector, so it could be in Rp, for example, but then you will always follow the gamma distribution. Okay, and we will use, of course, the Malliavin operators like Ciprian did previously. So my speech will be in three parts. We begin by explaining the Stein's method a little bit for the gamma approximation, which looks like very much to the Gaussian one, but it's quite different. So that's why we're explaining a little bit. Once again, in this speech, we will use the Wasserstein distance. This is a distance between two probability measures on RD, for example. And we will compare the expectation of f of x, where x follow, oh, sorry, typo. There's a mu2 and mu1 and mu and nu, sorry. So we will compare the expectation of f of x if x follow the first law mu, and f of y, where y follow the second law, mu indexed by 2 here, for f Lipschitz with parameter 1. So this definition is right here. So we will work with the Wasserstein distance. And the Stein's method for the gamma law is the same as the Gaussian one, meaning that we begin by showing a Stein's lemma, meaning if the following statement. So we consider z random variable, or very random variable. In fact, z will follow the gamma distribution with parameter nu if and only if for every smooth function. I don't precise the regularity of f, but for every f such that the expectations exist, we have this equality. And as in the Gaussian case, the proof of this lemma is only an integration by parts. With the Stein's lemma, we associate a Stein's equation which is an ordinary differential equation with the parameter h. We suppose here that it is bounded measurable, so that the expectation written over here exists. And we solve the differential equation over here, which is simply the difference between the terms that appears in the Stein's lemma. Okay, when we solve the Stein's equation, we can have a bound for the distance between a random variable capital X and a variable Z indexed by nu. And so the goal of the Stein's equation is to write differently the difference between the expectation of H evaluated in the random variables of interest. And in fact, we can write it as the expectation of a quantity depending on H with respect to F right over here. But the expectation in the right-hand side only depends on X and not on Z nu anymore. And consequently, we have a bound when we take H being Lipschitz, for example. If we can show that we can find a solution F depending on H, which belongs to a large graph of function capital A, we can in fact bound the Wasserstein distance between the law of capital X and the gamma distribution with parameter mu by this formula, the supremum over a certain class of function f of the expectation of it. And in fact, the Stein's method for gamma law can be extended, as I will show next. So I will explain here the independent Stein's lemma. This is something new we wrote in our paper. In fact, we compare Z and a real random vector capital Y. So the following are equivalent. Z follow the gamma distribution like the previous lemma, but something that is new is that Z is independent of the vector capital Y. And secondly, we have the same kind of equality with test function capital F, little f, sorry, which is in fact this equality. The change with the previous lemma is that the function f has two parameters. The first one, like the previous one, would be just a real parameter, but the second one would be a vector valued one. And in fact, we have this equality, which very looks like the case, the one-dimensional case where we don't have any random vector, but in this fact, we have the same, almost the same. We change the derivative with the partial derivative with respect to the first variable. And similarly, we can have a Stein's equation. This time, this is not an ordinary differential equation anymore, but a partial differential equation. We consider a parameter h, a two parameter function. And the Stein's equation will look like the following expression. So the right-hand side will be the one looking like the Stein's lemma for a dependent one. And the right-hand side will be the difference between the two functions h. And by the same computation we made before, little proof, which really looks like the Gaussian case. So suppose that Z follows the gamma distribution is independent of Y. Then just writing this expectation is the same as writing this one by the independence with a little notation f index I y. In fact, by using the very well-known Stein's lemma for the gamma distribution, we can write this equality, and once again by independence we can only have this. So the direct application is very easy, just integration by parts, no problem. And conversely, if we suppose that we have this equality for very large class of function f, then by just using the characteristic function, so we chose f to be complex exponential, we can have a differential equation for the phi, which is the characteristic function of the couple z y, and we have this differential equation, and knowing that we know the characteristic, the differential equation of the characteristic function of the gamma distribution, we conclude that, in fact, Z and Y are dependent and Z follow the gamma distribution. Okay, the proof very easy, looks like the Gaussian case, no problem on that. So we go back to our story. We have a Stein's lemma, we have a Stein's equation. So to conclude in a bound by using the Stein's method, we have to study the solution of this partial differential equation over here. Okay, and here we are. Proposition, we can study the solution of the Stein's equation. We can in fact prove that for every h, which is C1, with bounded derivative, in fact, we can find the solution f indexed by h, I just wrote by f right here, a solution so that every partial derivatives will be bounded by here the Lipschitz norm of h times the constant, which is explicit. Same bound here for the derivative with respect to every y parameters over here. And in the following, I will note C indexed by nu, the set of function so that satisfying those conditions, meaning that every partial derivative is bounded on R times RP with those constants appearing here. So we can study the solution of the Stein's equation, and so we can have a Stein's bound because we have this equality over here. And so we conclude that the Wasserstein distance, look, we conclude in a very general theorem, that the Wasserstein distance between a couple xy and the product between the gamma distribution and the law of y will be bounded by this formula. So by a supremum or a class of function, which is explicit, of this formula, the expectation of every term appearing here. Once again, the right-hand side, sorry, over here, only depends of x and y and not on a variable z, which could follow the gamma distribution, only x and y. Okay, so this concludes the first part about the Stein's method for the gamma distribution, and now we'll apply it to Wiener chaos. And this is here that we will where we will use the Malliavin calculus. So here we go. We define the Hilbert space H, where we can define the Malliavin derivatives. And we will suppose for the rest of the speech that x and y can be differentiable in the sense of Malliavin, and we suppose that x is centered. Then by the previous theorem, we need to focus on this term. And in fact, we will use the same trick as Ciprian showed earlier, meaning that x over here will be written as a combination of some Malliavin tools, Malliavin operators, and we will use some tricks about the Malliavin machinery. Here we wrote the duality relation, and here we will use the chain rule of the Malliavin derivative. What you have to understand about this equality is that we can write the quantity of interest which measure the difference between the two probability laws of interest only in terms of the derivative of f times some variables which could be quite easy to compute when x and 1 belongs to what we called the Wiener chaos. So there it is. We have a theorem which is quite general, I think, still yet. So we give x a real random variable, y a real random vector, sorry. We suppose that x, y, etc. are differentiable in the Malliavin sense. I don't precise what it is, but we just need to, we can compute the derivative of those quantities. Then we can show that there are two constants C1 and C2, so that the Wasserstein distance between the law of the couple XY and the independent product of the gamma distribution and the law of Y can be written as the sum of two terms. Difficult here to read when we don't know the Malliavin calculus, but in fact, we can read it as the following. The first term here is only showing the convergence of the of X toward the Gaussian the gamma distribution. The first term, in fact, is very often known when we do those kind of study. And okay, the first term doesn't use Y, in fact. In the second term, this is only the second term when Y is important, because the second term will show the decorrelation between the random variable X and every component of the real random vector Y. And well, this theorem is very close to what Ciprian showed earlier. And in fact, this implies yet for the gamma distribution. This is quite interesting. And we can apply it where X and Y are in Wiener chaos, which is the subject of the few slides which will come. To apply it, we will use a quite famous theorem, which is the force moment theorem proved by Nordin and Pegati. But this time it's not for Gaussian distribution, but for gamma distribution. So if I suppose that we have a sequence of random variable X indexed by n, which we can be written as I to Q, so meaning the integral, the multiple stochastic integral of order 2 times Q with a kernel G indexed by n, meaning that Xn belongs to the Wiener chaos of order 2Q for every n. So if I suppose that the second moment of Xn goes to something which is not 0, 2 times nu, then all the following are equivalent. We have the convergence to the gamma distribution over here, which is equivalent to something which implies, which involves the Malliavin derivative. So,
sorry, I to
yes,
Bessel function. What is I to Q? I?
Yes. I indexed by Q, meaning this is a multiple stochastic integral with respect to a Brownian motion, for example. So I always define the stochastic integral with respect to a certain Wiener process. In fact, when I write I indexed by Q, you can imagine that this is 2 times Q iterated integrals of Gn. So Gn, this is a function with 2 times Q parameters times every Brownian motion coming over there. And there are 2 Q Brownian motion which I integrate over there. Does it answer your question?
Yes.
Okay. Don't hesitate to stop me if you have any question. It's a pleasure to answer. Okay. So, okay, we have those equivalents. The third here equivalence is quite interesting because the convergence in distribution is only equivalent to the fact that the third and the fourth moment converges to the moments of the gamma distributions one, which is very interesting and quite mysterious. We have the same, of course, for the gamma distribution, for the Gaussian distribution. We have the same for the gamma distribution. And finally, one technical here conditions I will not explain. It will spawn everywhere. If you have any question, we can talk about this later. But this is only conditions about the kernels appearing here in the definition of X indexed by n. And in fact, the condition number D which will be the one which will be appearing in the main theorem we wrote with Ciprian, which is the following. So I gave x indexed by n, a sequence of random variables belonging to the order, the Wiener chaos of order 2 times q. I give a random vector. Okay. I suppose that the random vector also belongs to some Wiener chaos, q indexed by j. And we suppose some minimal condition, I think. The first one is that xn converges to the gamma distribution, that the random vector yn converges to something. And finally, that we have asymptotic decorrelation, so meaning that the expectation of xn times every component of the random vectors goes to zero. And one more technical condition coming from the force moment theorem I explained just in the previous slides. If we only suppose that, well, in fact, we can conclude that we have convergence in distribution to the gamma distribution times the law of y. In other words, we have asymptotic independence between xn and yn. And moreover, we have an estimation of the Wasserstein distance between the two distributions, which very looks like to the what I already shown. And with one last term over there, showing the convergence of the random vectors yn to y. And in fact, we have two terms, so only involving the convergence of every marginals of the couples xn and yn. So this one is about the convergence of x. I forgot to write the n over there. The second one is over there about the convergence of yn to y. And only this term, the central term here, is only about decorrelation. And this is only this term over there, which in fact show the asymptotic independence. And we can compute, in fact, this term by using the third correlation I write over there in blue. Okay, so this is the main theorem. We have only three conditions, two conditions which is quite natural.
Q product. What is it? Q product with Q. Product, yeah.
Yeah. The product of the gamma distribution. No, over the law of y.
Product with Q. What is it?
Where is Q? Yes. Oh my God, I forgot. I think there is a factor Q over there. Yeah. You're right. Well, this is very important that x and y belongs to the Wiener chaos. Okay. I think this is there is a factor 1 over Q In fact, it depends of Q. Okay. Yeah, I just forgot to write. I'm very sorry for that. I think there is a constant going over there in the scalar. No. In fact, okay. Sorry.
There is no Q. There is no
I'm
Q.
right. I'm right.
Hidden. Q is hidden in the derivative.
Yes, it is hidden because Q will appear when we compute the derivative of x and the derivative of y. In fact. For example, xn over there, if we compute the derivative of xn, there will be a 2q times the derivative of this thing, which would be an integral with order 2q minus 1. So in fact, the q appear in the derivative over there.
Thank you.
Okay. Thank you for your question. This is a good question, in fact. So, okay, in the last few minutes, I will just I will show you an example of how we can use those conditions, how to compute practically for some example to show in concretely show the convergence mentioned in this theorem. So here we are. The example is over there. I consider a Venn process. WT over there on 0, 1. And for every n over there, I will consider this sequence of integrals, of Wiener integrals, meaning that we compute the integral of two deterministic functions over there, the two cosine right here, and we integrate it with respect to this Wiener process. And I will take the sum of those integrals. And un can be interpreted as an element of the second Wiener chaos by writing that this is I2 indexed by Gn, where Gn is this function over there. So here we really see an element of a Wiener chaos really like a double integral with respect to a Wiener process over there. Okay, so this is the example. It is known that un converges to the gamma distribution with factor 1. And even better, we have an estimation of the Wasserstein distance between un and the gamma distribution, which is given by a constant over here, square root of n. Okay, and in fact, in this example, we will prove that un and a random variable y, which could be interpreted as a second Wiener chaos element, a second multiple integral with a certain function C1 over there, will be asymptotically independent. And in fact, y is involved in un, because y, if we compare un and y, in un, if you take I equals to G equals to 1, in fact, we get y. And we will show that when n is very high, there is a lot of terms involved in un. And in fact, when n will be very, very big, un and y will be independent only just by using the previous theorem. So we know that un converges to the gamma distribution. Y is fixed, it doesn't depend on y. We only need to show the third condition about the decorrelation one. So this is what I wrote over there. We need to compute the decorrelation between un and y, and the more technical term involving the kernels of un and y. And we need to prove that both terms go to 0 to conclude the theorem. And in fact, we can prove that this is decorrelated for every n. The expectation is equal to 0. And we can compute the second right term, the second term right over here, which goes to 0 as n goes to infinity. And just by using our theorem, this is quite easy to prove that we conclude in the asymptotic independence. And better, we can have an estimation of the Wasserstein distance between the couple un-y and the asymptotic law, the gamma distribution times the law of y, and it will be the same speed as un to the gamma distribution, meaning square root of n. Okay, so I will conclude my speech by making a little summary of what we did. So in the first part, we developed a Stein's method for the law, for every law of the type gamma distribution times another probability law. Okay, for a large graph of probability, we only suppose that the variable we consider are Malliavin differentiable. And by using the Stein-Malliavin method, we give a general theorem giving an estimation of the Wasserstein distance between the couple xy and the target law, so meaning the gamma distribution times the law of y. And finally, we applied it for the Wiener chaos case and giving some very easy conditions to check to conclude that we have convergence distribution and asymptotic independence. And this is the end of our speech. And thank you for your attention and for your question. And don't hesitate to question me if you have any question.
thank you for your talks. Both talks are very important and interesting. Dear colleagues, please, your comments. Or
I have some questions, if it's possible. First question is the following. Theorem about the fourth moment, which was given first in Jourdain and Piccati, is a little bit mysterious.
Sure.
Do you have some explanation that for estimation of the corresponding distance only is sufficient ask about the convergence of the fourth moment to something? Why only fourth moment?
So maybe I try to respond because, yeah, it's a very interesting point. So let me recall that, yes, if you have a sequence on Wiener chaos, this sequence converges to Gaussian if and only if the four moments goes to 3, okay? 3 is the fourth moment of the Gaussian distribution, standard normal Gaussian distribution, right? So yes, very important result by Noalart and Peccati. And what happens here, you know, that basically to prove the convergence to Gaussian distribution, you have to prove the convergence of the first second moment, no? First and second moment, okay? And well, the expectation of the fourth moment, if you write the expectation of the fourth moment minus 3, okay, show you that as it's sum of sum of squares, and it's a sum of squares. So it's actually from this formula, from expectation of the fourth moment minus 3, you have that as the third moment, the fourth moment, as the moment of your distribution goes to 0. There is some product formula on Wiener chaos. I'll show you this. Okay, so this is a possible explanation. I don't know if you, Jérémy, can.
Yeah. In fact, the first explanation can be only because the product formula on Wiener chaos is quite interesting, important, and this is because this formula exists, that in fact the second and fourth moment control everything in a Gaussian case. But I think there are a lot of papers right after that just trying to explaining the fourth moment theorem, how mysterious these conditions are. And in fact, we look for the universality in some case of the fourth moment theorem, meaning that we saw in my speech that for the gamma case we have the same kind of theorem. So this is quite mysterious. In fact, how to answer properly to this question? Not easy, because for example, if you think about a paper of Michel Ledoux in 2012, I think, he gave an explanation using the Einstein-Uhlenbeck operator. And in fact, when we know how to diagonalize and how to decompose the space L2 by using the kernels, the eigenspace of L, the Einstein-Uhlenbeck operator, we can conclude of it. This is just very, very difficult question. In fact, there's no easy question, so we can give a lot of questions. I think yet we don't have a very good answer, easy and quick answer to that question. But this is very, very passionate question.
In fact, if you consider no integral integral of arbitrary order.
Yes.
Arbitrary order. And so it from first glances, I thought that it's necessary to think more convergence of the next moments also. But in this story we have only fourth moment. It is a little bit mysterious.
Yes.
Okay.
Actually, you have the second and the fourth moment, okay? You have the second also, it's important, no? Second and fourth.
Yeah, second and fourth. Yeah.
Second. You also need the conversion of the second moment to the variance.
The second question is the following. What do you know about the method of Stein for estimation of the closeness of the conditional distributions? I can explain you. Now, for example, let's consider on interval 0, 1, Brownian motion. And if we consider distribution of this Brownian motion under condition that in time 1, under condition that model of the B1 less or equal epsilon. Now, when we know that then epsilon converges to 0, the conditional distribution converges to the distribution as Brownian bridge.
Okay.
Yes.
Yes.
It's one definition.
Yes.
But I want to estimate rate of conversion. And so the question is, does exist something in this direction?
As far as I know, no, because not at least not Stein-Malliavin calculus, because if you have conditional expectation, it's very hard to differentiate in the Malliavin sense. So, but your question is very interesting. So I don't know if I can quantify this converges to Brownian bridge, but very interesting point. Yes. Yeah.
In fact, it's a very simple question.
It's really simple. Yes, yes. But well, yeah. Maybe not so simple, huh? Simply to ask, but not simply to answer.
Yeah, next questions, please. Next question, Yelena.
Yeah, maybe some comments or questions or something else. Maybe some.
And by the way, that's first my question. And so, gamma distribution belongs to the Pearson system. Yes, one Pearson.
That's true. Yes.
Yes.
Pearson system. But a lot of distributions, in fact, better, and so on. And so probably work is going also in this direction.
Yeah.
No, here there works. For the one-dimensional Stein method, at least, if you want to approximate distributions, the Pearson class, yes, there are some works with some general bounds. Yes. I'm not an expert. I didn't work on this, but I know there are works by, I don't know, Frédéric Viens, for example, from Rice University.
But
so, yeah.
yes, of course, it's interesting simply to start with the Pearson distributions. Density is a ratio of one polynomial to another polynomial.
But there are several works in this direction. Pearson class.
Okay, you understand, yes.
Yeah.
Maybe another questions, please. So thanks one more for your talks, and I would like to say that.
And I want to say that today, this meeting, your talk was very popular. We see that 49 people attended in your talk.
We're very glad. Okay, we're very glad.
Yeah, thank you.
We say hello to everybody. Yes.
Sure.
Thank you once more. And your talk, it's possible to hear on a site of our seminar.
Of course, we play. Yeah.
And now I would like to announce our next talk that will be on the next Wednesday. It is a talk of Ekaterina Polomarchuk from High School of Economics on nonlinear ergodic optimal criteria for linear stochastic control systems with variable coefficients.
So we invite you also to participate. You know our Zoom. you know our zone, and so you can participate.
Yeah.
Thank you very much.
Я скажу для наших слушателей русскоязычных, доклад Екатерины Полумарчук, это молодая доктор наук, она еще никогда не выступала на нашем семинаре, это будет ее первое выступление, о неэргодических критериях оптимальности для линейных стохастических систем управления с переменными коэффициентами. We will wait everybody on our next seminar. Thank you very much.
Thank you very much.
Thank you.
Thank you very much.
Next time.